Welcome back. This is the second video on using maximum entropy methods for statistical analysis. The previous video in the preface discussed roughly from a high level what MaxEnt is and why you might want to learn it. And this installment is intended as a soft introduction to the basic nuts and bolts of maximum entropy. This is going to be very gentle, maybe to the point of even being a little bit unsatisfactory, because we will need to do examples to put these things into action, and that will take place in the next few videos. So at the end of this, you should have a decent conceptual idea of what the workflow looks like for these types of analyses. Okay? This video and all the videos in this series are meant to accompany a much larger and more in-depth course that I've created, and if you're interested, you can find a link in the description below. Okay, so the basic idea behind maximum entropy, which we discussed a little bit in the preface video, is to maximize entropy, unsurprisingly, which is a measure of uncertainty, subject to the information that is contained in our data, as well as certain selected restrictions. So by restrictions, I mean features of our data or our data generating mechanism that we at least conditionally assume to be true. Okay? And we'll look at these restrictions in more depth as we go along. But we can imagine the process of MaxEnt as something like starting with maximum uncertainty and then mixing in some information that is contained in the data, as well as these restrictions that are a little bit nebulous at this point, but which we will make concrete shortly. And that information shapes, reduces the uncertainty. That's the basic idea. All right. Now, of course, different information contained in different data and different restrictions will lead to different probability distributions. And again, it's worth remembering why we want to maximize uncertainty, entropy, in the first place. It's because if we're doing anything other than that, if we're not maximizing entropy and reducing it only to the extent that we have information that justifies doing so, then it is the same thing as adopting beliefs, call it, but information that we don't actually have, and therefore have not verified, have not made any assessment on one way or the other. And if we want to learn about the world or a system or whatever is of interest, we probably don't want to make assumptions that are unjustified. It's also just worth reminding ourselves that at the conclusion of the MaxEnt workflow, or maybe not the conclusion, but one of the things that we get out of the MaxEnt workflow is probability distributions. And if the restrictions that we select just happen to be of particular sets, we get back these familiar closed form probability distributions, like the binomial and then Poisson, etc., etc. But if we happen to select a set of restrictions that do not align with these closed form distributions, without MaxEnt, or I should say without computing power, we would just have to, cut our losses and adopt one of these distributions. But what MaxEnt allows us to do, combined with computing power, is to find probability distributions, solve for probability distributions that don't have closed forms, right? That are bespoke to the assumptions that we hold about our data. And that makes it incredibly powerful and incredibly flexible. Okay, so now we're going to start getting a little bit more rigorous about some of these terms. And the first one is entropy. Okay, and so to this point, we've relied on calling entropy a measure of uncertainty and then just relied on the intuitive understanding of what uncertainty means to kind of carry our explanation. But that idea still holds, but we're going to frame it slightly differently because a slightly different framing maps onto the mathematical expression of entropy a little bit better. And so what we're going to find as we go through this slide is that entropy is the weighted average of surprise. Okay. So first I'm going to show the expression for entropy. It's usually denoted with a capital H of the random variable, here y, the outcome variable y. And for a discrete random variable, it is a summation of, well, you can see what it is, the probability of y times the natural log of 1 over p of y. And of course, for continuous distributions, we would just integrate. And if you know your properties of logarithms, you know that that middle expression is the same as the right-hand expression where we take the negative sum of probability of y times the log of probability of y. Okay. Now, if this is your first time seeing this expression, then it may seem unmotivated, but when you kind of get your tires on the track here, you see that this is a completely intuitive mathematical expression. And it starts with this expression that's highlighted in blue in the parentheses, which is 1 over the probability of y. And we're going to call that surprise. And this is a very good name for that quantity. So think about it like this. The maximum probability of something is 1. So if we have 1, probability 1, then surprise here is 1 over 1, so we have 1 unit of surprise. Well, what if the probability made that event less likely? Call it 50%. Well, now how much surprise do we have? Well, now we have 1 divided by 0.5, which is 2. So we have more surprise. And as we continue to drive probability lower and lower and lower, when that event occurs, it is increasingly surprising. So hopefully this idea of surprise makes some intuitive sense. Now, how often, if we look at a lot of instances of y, how often will we be surprised by p of y? Or 1 over p of y? When will we experience that much surprise? Well, we experience that much surprise whenever p of y happens, which happens with probability p of y, right? Or whenever y happens, I should say, not when p of y happens, when y happens, which happens with probability p of y. Okay. So hopefully you see where these terms are in the expression for entropy. We have p of y multiplying the log of surprise, and we won't worry too much about the logarithm here. It just happens to make everything additive instead of multiplicative, which is very nice. That's why this expression uses logarithms, but the story still holds here. Now, if we do this for every y value and sum them, what we get is the average surprise across y. And that's what entropy is. It's the average log surprise of a system, y. Okay. So when we compare low entropy systems versus high entropy systems, you notice that a low entropy system will have some very improbable events that are going to be very, very surprising. It's just that they happen so infrequently that their overall contribution to the total surprise is not as much, or not very high. Conversely, high entropy systems are going to have a lot of moderately surprising events. Okay? So they're moderately surprising, they happen with moderate frequency, and so total surprise, total entropy goes up. Okay? Now, the low entropy system, by virtue of having few highly probable events, is more predictable, right? Because so much probability has been concentrated into a few different possibilities. So it's more predictable. Conversely, high entropy systems are less predictable because so many things are similarly likely to happen. Okay? So if we take this language of predictability and flip it over, we get back to this idea of uncertainty, right? The more predictable system is less uncertain. The less predictable system is more uncertain. Okay? So hopefully you see how this mathematical expression maps all the way through back to our intuitive understanding of what entropy was in the first place, which is just a measure of uncertainty, or conversely, a measure of average log surprise. Now, just briefly, we'll mention that there are other types of entropy, right? So we've been talking about the entropy of a single variable, y, but if we were considering multiple variables, then we could discuss their joint entropy. Just as we have a probability of y and an entropy of y, we have joint probabilities and conditional probabilities, and they correspond to joint entropies and conditional entropies. We will return to this later in later videos, but just to kind of flag why this is relevant. So for instance, conditional entropies, this is how we will do the, I shouldn't say equivalent, but the MaxEnt analog of regression. Okay? So whether or not it's been framed for you in this way or not, but when you're doing regression, you're dealing with a conditional probability problem. Okay? And so similarly, we will use conditional entropy to find the relation between explanatory variables and outcome variables, which is just regression. Okay, so we just discussed entropy in some detail, and now we'll talk about these different restrictions. We have different types of restrictions, and the first type is what kind of data are we working with, discrete or continuous? Okay, that's going to determine what probability distributions are available to us. There's also the domain of the data. You know, what possible values are available, right? And again, that's going to determine what type of probability distributions are available to us. And then there is this idea called constraints, and that's a very unfortunate name because constraints sounds a lot like restrictions. But we'll look at constraints here in a moment. I mean for constraints to be a more specific idea than restrictions. Constraints are a type of restriction. Constraints are generally information that can be packaged as the expected value of a function of a variable. That's a mouthful, but we'll see some examples here, I think, in the next couple of slides. Okay. So what do constraints look like? Well, this isn't much better as far as clearing up our understanding because this is a very weird looking expression, but you'll see that it's actually very simple. But constraints are some relationship between some accepted value, some constant usually, that I'm calling here k, and then the relation is represented by the circle, where that circle could be equals, greater than, less than, something like that. Some expression, where that expression is a model-derived quantity that can be expressed as an expected value. Here, the expected value of the function g of y minus an estimate of g of y, which is g hat of y. Okay, so just set that on the table, and we'll unpack that a little bit and see how it plays into this broader framework here, right? This is just a piece, and we're going to fit this into the entropy here soon. Okay, but let's just give a simplified example of a constraint, and that is the mean constraint. Okay, so let's just march through this here. So here 0 is k of j. The circle is equals. Okay, that is the relation between the left-hand side and the right-hand side. Now we have the expected value of a function of y, and in the mean constraint, the function of y is just y itself minus an estimate of that function. And it just so happens, if you're not familiar with moments, the first moment, which is being depicted there, is the is the mean of a distribution. And we use a hat because it is here estimated, okay, from the data or some other means. Okay. So this is a very typical constraint. So hopefully by seeing something like this, it makes the left-hand expression there a little bit more easily digested. So there are many different targets of these constraints. Here we're using a moment, and in fact we will typically use moments. I think almost exclusively we will use moments. The book itself has an appendix that discusses how to use other types of constraints, but moments are so flexible that we will really focus on them. But we could use other things like quantiles and absolute values and indicator functions. And again, the book has an appendix on those things if you're interested in them. I keep saying book, but of course I mean course. Okay. So how do these constraints and restrictions and entropy, how do they all play together to eventually produce a probability distribution that maximizes entropy? Well, the answer is that they get packaged together in this mathematical object called the Lagrangian, represented with this scripted L. And the Lagrangian is just simply the entropy, H, which we saw earlier, minus all of our constraints. Okay? All of our constraints here. And each of these constraints here these are in the parentheses, right? That's a constraint here. I should say, I should have said, okay, in the previous slide I said that this is equal to some value. Okay. Well, what we end up doing is we set that value to 0, like we did for the mean constraint. And so we don't write the 0 here, but we could write the 0 there. Okay. So anyway, so we have our set of constraints, and each of these constraints is set off by what's called the Lagrange multiplier, these little lambdas. And for right now, it's enough just to know that these lambdas, we estimate them, and they act as little dials to increase or decrease the importance of any particular constraint on the distribution that we solve for. Okay. Now, remember, there's other types of restrictions. There's the type of data, and there is also the domain, and those things get packaged in the expected value, right? So if we have the expected value of a discrete distribution, then we're using summation, and we're summing over the domain of the variable, right? So those things get packaged in the expected value here. Here I've just simplified the expression, and we'll see examples later that will make that more concrete. And also what is hidden here is the probability of y. That's going to be important because we're going to quote-unquote solve the Lagrangian. Actually, we're going to solve the derivative of the Lagrangian to find p of y. And so the p of y's are hidden in this, in how I've written it in the entropy and in these expected values there. But they're there. Okay. So we'll kind of see how we use the Lagrangian here in a moment. But for right now, let's just kind of see why an expression like this might be what we're after. Okay. So again, we're trying to find the distribution that maximizes entropy. And you can see kind of what's going on here. We have the entropy of our system, and then we're subtracting off entropy insofar as it is justified to do so by our data or our restrictions, right? Our data is represented, in these estimates of the functions, for instance. So we're balancing the entropy of the system with the information contained in the data and in our restrictions, right? We're literally subtracting off entropy based on the information contained in those ideas, or in the data and in the restrictions. Okay. Now, again, we actually need to find the probability distribution. It's nice to have a Lagrangian, but we actually want to use this to find the probability distribution. And the way that we do that is we take the partial derivatives of the Lagrangian with respect to each probability of y and set it to 0 and then churn forward and solve for the probability of y. Now, this expression here in the middle, just take it as a token representation of this concept. Again, we will work through specific examples that will make this much more concrete. But that is the basic idea. We take the derivative of the Lagrangian, the partial derivative of the Lagrangian with respect to the probability of y for each y, and then that gives us an expression for the probability of y that we then go forward and solve. Okay, so this introduces an overall workflow where we write the Lagrangian by writing first entropy and then second the restrictions, and then we take the partial derivatives of the Lagrangian with respect to each p of y. That will give us a term where we can then solve for p of y. Okay? That is the overall workflow. Again, just take that on board as a high-level overview, and I think as early as the next video we will begin to actually implement this and solve for actual probability distributions. Okay, that is it for this one.